This is round 2 of my super quick reintroduction into making videos for me in my upstairs location instead of the basement. What I want to look at real quickly is kind of a visual representation of why the law of conservation of mass is necessary for chemical equations, why we balance chemical equations. And again, it's something that I don't immediately think of, but one of my students asked a great question the other day, which is why, if you have something, for instance, like hydrogen and oxygen giving you H2O, why do we have to put coefficients in front of that? Why do we have to go back and fix our lies? And we'll look at this with straight up balancing. As we look at it, hydrogen and oxygen, we've got on the reactant side 2 and 2, on the product side 2 and 1. And so the oxygens don't match. And I want to look at that in a slightly different way, which is to say we've got hydrogen, and we've got oxygen and oxygen. And it's going to make an oxygen with a hydrogen, and we're going to have an oxygen left over. And we know we don't, the reaction's got to have all of that stuff used up. It's kind of like oxygens come in a 2-pack from the store, and you don't just get to use one of them when you get them home. So in order for this to work, I'm going to need 2 more hydrogens, and so I'm going to need 2 of those there, and as a result, I now have 2 waters. And that's how our balancing with coefficients works over here. We've got now 4 hydrogens there and 4 hydrogens there. So it's not that we're lying and putting these coefficients in, it's that we're telling the truth that we need to use up all those pieces. And sometimes it's a little easier than others, and I'm just going to sketch this one out much smaller. Say you've got something like hydrogen and chlorine giving you HCl. If we set up our table of reactants and products with hydrogen and chlorine, we've got 2, 2, 2, and 2, if we put a 2 right there. But this makes sense. It's not that we made 1 HCl. We've got hydrogen and chlorine with chlorine. And we're going to make a hydrogen with a chlorine. And we've still got another hydrogen and another chlorine. All right? So in this particular case, 2 hydrogens, we used them both, 2 chlorines, we used them both. And it's actually kind of interesting if you look at it in terms of the overall mechanism, but it's a different video for a different day. The last one I wanted to glance at here is something a little different with ammonia. So say you've got nitrogen and hydrogen, and it's going to make ammonia NH3. All right? We're going to fake the balancing again. I've got nitrogen, and I've got hydrogen, and I need to make nitrogen with 3 hydrogens. Well, if I had 1 nitrogen and 1 hydrogen, that's what I would end up with. As it stands, I currently have this picture, and let me scoot this up just a little bit. As it stands, these are the pieces I currently have as products. A nitrogen not bonded to anything, and then a nitrogen with 2 hydrogens and nothing there. So let's say we have another hydrogen here. That gives us that, and now we have a hydrogen there. And then you say, okay, well, I've still got 2 bonding locations. I'm going to need another pair of hydrogens. So at that point in time, I've got 1 nitrogen, and I've got 1, 2, 3 pairs of hydrogens. And then I end up with 2 NH3s. And if we look at the balancing of that real quickly, we've got nitrogen and hydrogen. Reactant side, we had 2 and 2. Product side, we had 1 nitrogen and 3 hydrogens. So 1 nitrogen and 3 hydrogens. And so in order to make this work, we're going to need to somehow fix this 2 and this 3. Least common multiple is 6. So I'm going to need 2 here, which will give me 2 of those and 6 right there. And then a 3 there to make it work. We end up with 6. So visually, that may be a little easier to see, which is build the pieces as it goes.